Thanks for inviting me. This is joint work with my student Mika Göös, who's responsible for a lot of the great ideas in the paper. I was the one who pushed this problem and had some of the initial ideas. Okay, so let's talk about communication complexity. Everybody probably knows what two-player communication complexity is. You have a problem F on joint input X and Y, and you have two players, and they're trying to communicate back. They communicate back and forth through a shared blackboard, and they want to agree on a function F. And the complexity of a protocol is the number of bits exchanged between them to agree on the function value. And we're going to be interested in randomized protocols. And the lower bounds, of course, have tons of applications in computer science, and intuitively they show an information bottleneck when the input is disjoint. The number one forehead model is even more interesting, and now you have a bunch of people, and they have their input placed metaphorically on their forehead, so the X player can see everything besides X. And again, they're trying to compute a joint function of their inputs, and they communicate again through a shared blackboard based on an agreed upon protocol, and they're trying to compute a function. So today I want to talk about search problems, which is less studied than decision problems. So I want to talk about the communication complexity of search problems. And these have a history starting with Wigderson in '88, where they showed that certain search problems are fundamentally basically equivalent to the question of circuit depth. And they also come up in proof complexity. You can show that certain search problems, two-party communication complexity lower bounds for the search problems, give you like rank or depth bounds on certain proofs. And if you switch to if you're able to get number on forehead lower bounds for communication protocols, then you get rank bounds for more complicated proof systems. And you also can get some like length space trade-off for certain proof systems. Okay, so what's a search problem? A search problem, the only difference is that you have n inputs as usual, but now you want to output some solution, some little q in capital Q. And so for a given input alpha, you could have more than one solution. Certain assignments, alpha, there's special ones that are called critical ones, and those are assignments where there's only one legal answer. Okay? If all the assignments are critical, then it's just a function. So a measure of difficulty of a search problem was given by Huynh and Nordstrom in STOC 2012, and it's a variant on block sensitivity. So just to remind you, the block sensitivity of an ordinary function f, so the block sensitivity of an input alpha is you look at the maximal number of blocks that you can find, disjoint blocks in alpha, so that when you compute f on alpha, it takes on one value, but if you flip all the variables in any given block, the value of the function changes. Okay? And for a given alpha, the largest number of disjoint blocks that you can find, that's the block sensitivity of alpha. And the block sensitivity of the function is you take the worst case over all assignments alpha.
Go with what slide?
Yep.
Okay, thanks. So what does mean function f realizes search problem?
So I'll get to that I'll get to that in a second. So it means that for every alpha, it outputs something that's legal. That's one of the legal answers.
Oh, great. Probably was saying that block sensitivity was introduced by Nissan, and that it's really important.
There we go. Yeah, it's very important. Yeah, it's a standard measure. It's polynomial equivalent to lots of other cool measures like decision tree complexity, polynomial approximation degree. Yeah, it's a fundamental concept. And you can also define block sensitivity of a search problem where you just take all functions f that realize the search problem, and then you look at the minimum over all such f of the block sensitivity of f comma alpha.
Block sensitivity is, so now you don't have a function.
Right, so when you have a search problem, I want to take the minimum f. Right. So if you have an algorithm that computes the search problem, let's just assume for now that it's deterministic. They won't be. It'll solve the search problem by coming up with a function, and so you want to take the minimum over all functions. Okay. No, f is in this whole talk. F is not Boolean.
So even if don't count it all toward the block sensitivity of that?
I'm not sure I understand the question.
If you say maximal over all critical assignments, so if an
Oh, I didn't get to this one yet.
Oh.
Yeah, so, okay, you can ask your question in a second. So, so what I said before, an assignment is critical if there's only one answer. And the critical block sensitivity is we're only interested in the, when we do the whole definition, we only do it with respect to the critical assignments. So you could have an assignment that's critical, and when you change a block, it'll become non-critical. So you have to deal with that still. But you don't start with an assignment that's already has more than one answer.
Yeah, my question is, if you have an assignment that has only two answers, then even then it is not counted at all
Right.
to other blocks.
That's right. That's right. Yeah, it would be we would be really happy if we could figure out how to do all this without critical. But anyways, we'll get there in a little bit.
Critical at least gives you a definition of what the function is at the assignment.
Yes,
So
and
that
it's
you
very
can
helpful for.
automatically change.
That's right. It's very helpful to you'll see in a minute why it's really a great definition to get applications. Okay. So in general, this is something that's very popular and very convenient to do if you want to talk about the communication complexity of a search problem and get a lower bound. A very common thing to do is to compose it with an inner function. So you have the original search problem S on n variables, and what you do, these are the original inputs, and you replace each one by a little function g. Think of it as on a, if we're doing in the two-player setting, it'll be a function g on, say, 2 inputs, or maybe a constant number of x inputs and a constant number of y inputs, and then you feed in the output of the g's to the s. Okay, so you're just substituting in the g's on disjoint inputs for each of the original variables. Okay, and that's the notation for s composed with g of n. And then now you can think about, you don't have to do this. You could have originally partitioned the original variables into 2 pieces and talked about the communication complexity, but it's much harder to prove those lower bounds. So in general, this is a setup. I don't really know who started it. I know that it was in Roz McKenzie's paper. It's been in tons of papers, not just in communication complexity. But anyways, it's much easier to prove lower bounds when you consider these composed search problems. So those are the ones we're going to be looking at. And now in the communication setup, you'll give Alice the x's and you'll give Bob the y's, and you want to compute the composed problem. Okay? So we're going to show communication complexity lower bounds for composed search problems in the 2-player and in the number on forehead setting. And some prior results that are most related are this paper that I already mentioned by Huynh and Nordstrom, and they proved the same sort of result for k equals 2 players with a different proof, with an information complexity proof. And then an old paper by myself and Paul Beam and Nate Segerland, we proved a special case of this result for k roughly log n players, but it was really specific to a specific situation, so we weren't able to get very many corollaries from it. This proof I'm going to give you today is really simple. It's a reduction to unique disjointness. And so basically we show that the randomized communication complexity of the composed search problem is as hard as unique disjointness on m variables, where m is the critical block sensitivity of S. And the real trick in getting this result is that to pick a really good g, the inner function.
Oh, so it's for every function, for every problem S, there exists some function g.
Yeah, we're going to use the same g's. I'm going to give you good g's, and we're always going to use those g's.
Yes, but it's not for every g and every s.
No, for every s, there exists a g.
Okay.
Yeah. Okay, so just specifically, the two-party theorem is that if there is a two-party function g, such that for any search problem S, the complexity of the composed search problem is going to be exactly omega of the critical block sensitivity of S. And this is the randomized complexity. And and for the multi-party case, because so I got rid of disjointness because the lower bound for disjointness is optimal. So for the two-party case. And for the multi-party case, I did not get rid of disjointness because the best lower bounds currently are due to sure stuff, and they look like square root of n over 2 to the k times k. So it's gets a little bit uglier, so I stated it just in terms of in terms of disjointness. So if you have, there is a k-party function, G, and the domain size grows. It's every player gets k to the little o of 1 bits, such that for any search problem S, the randomized complexity of the number in the number on forehead model of the composed problem is exactly the randomized complexity of unique disjointness on, again, on M variables, where M is the critical block sensitivity. Okay. Okay, so I'm going to tell you how you get the search problems. They're going to come from unsatisfiable CNFs or unsatisfiable CSPs. And then I'll tell you about two specific really nice ones that we're going to use. And I'll show you that we proved that they have high critical block sensitivity. And then I'll quickly tell you about the applications, and then I'll tell you about the proof. Okay, so here's how the most common way to get a search problem. You start with an unsatisfiable CSP called capital F, and D is the number of variables in each constraint. And these are going to be usually Boolean, so you can think of them as Boolean CSPs. And if you start with one of these unsatisfiable CSPs, the canonical search problem associated with it is you're given an assignment alpha to the variables of the CSP, and you want to find a constraint that's violated. Okay. Okay, so these are the two we're going to be most interested in. Again, it doesn't matter what the theorems hold, no matter what the search problem is, but these have nice critical block sensitivity properties. So Tseitin is an unsatisfiable CSP where you start with a graph G, an undirected graph on an odd number of vertices, and think of it as being a constant degree graph. We'll take ones that have high expansion properties. And the Tseitin CSP will have variables for all of the edges, and you'll have one constraint for every vertex, and the constraint will say that the mod 2 sum of the edges incident with that vertex should be odd. And so k-rootability is a particular property that very highly expanding graphs have for large k. Yeah, it's unsatisfiable. I guess I could do that. It's unsatisfiable because you're counting the edges in two different ways, right? You can count the edges in two. You can count them coming out of. You can sum up all of the charges for all the vertices. That's like counting every edge twice. But on the one hand, it's going to be odd since there's an odd number of vertices. But on the other hand, we're counting each edge twice, so it's even. Okay. That's another way to say it. Right. It's actually, the Tseitin principle is slightly more general. Usually you put a charge on the vertices where the total sum of the charges is odd, but it's not really, doesn't matter too much. Okay, so a graph, we'll call it k-rootable, and this is slightly different than the usual definition. If there's a set T, a subset of the vertices of size 2k, or bigger than or equal to 2k, such that for any pairing of the vertices in T, there's edge disjoint paths connecting the pairs. And what we show is that if you have a graph that's k-routable, then the critical block sensitivity is omega k. And for sufficiently strong, there are sufficiently strong expander graphs of constant degree that are n over log n routable. And so we get critical block sensitivity of certain nice graphs, bounded degree of n over log n. Okay? So this is very high critical block sensitivity. Another example that we'll see is the pebbling. These are not our examples, by the way. These are around in all the literature, both of these examples, and for good reason. The first one because it's, you start with a graph it has very high critical block sensitivity, and this one because you can get a tight upper and lower bound on the critical block sensitivity that can be useful to prove like hierarchy theorems and things like that. So pebbling, you start with again a graph, but now it's directed. And again, now you want the in degree to be bounded by D. And PEB-G is a CSP where you have variables for all the vertices instead of all the edges. And you say that all of the source vertices are true. And you say that there's one sinc vertex, call it T. You say the sinc vertex is false. And then you say that the true-false thing respects the graph. So for every intermediate vertex, if its children are true, then it's supposed to be true. Okay, so that's like some kind of induction. It's clearly unsatisfiable. And we prove that there's bounded degree graphs on n nodes such that the search problem associated with has deterministic decision tree complexity square root of n, and the critical block sensitivity is also lower bounded by square root of n, upper and lower bounded by square root of n. Okay, so this was for different graphs, G, for pyramid graphs, this was known to be true, but with weaker choice of parameters. So I think it was maybe n to the fourth instead of square root of n. So we don't use pyramid graphs, we use a fancier type of graph. No, I don't know that. I don't know that. I don't know how to improve this construction, but that's a good question. Okay, so almost for free we get some nice results, although they were already known. We slightly improve the parameters. But the best monotone depth bound for an explicit monotone function in uniform NP was n to the half, and we get n over log n using the Tseitin. And the best monotone depth bound for a monotone function in monotone P was n to the sixth, and we get square root of n. And we do that one using the pebbling examples. And we also get, with a little extra work, these bounds holding in the average case setting. But by average case, I don't mean over the uniform distribution. I mean that I'm going to pick the distribution, and then over that distribution, we get good average case lower bounds. And one thing that I think is open that's really interesting is this result here. I think that even if you were willing to go to a non-explicit monotone function, I don't think it's known how to beat the square root of n. Correct me if I'm wrong, but I think it's not known how to beat square root of n. So if you want to come up with the worst case depth for a function that's in monotone P.
Oh, okay, I see.
Matching is a function, but we don't know this is monotone P and it's useful.
Okay, so another application is it's related. It's oh, sorry, I already told you the applications about circuit depth. So now I'm going to tell you briefly how you get this from the main theorem. So in this paper by Ross and McKenzie, they stated, like the last sentence of the paper in the conclusion, something that I didn't notice until about a month ago, which was, in general, people have used Karchmer-Wigderson to show that if you have a monotone function, you can get a search problem associated with it where the complexity of the search problem is equivalent to the depth. But Ross-McKenzie actually showed that you can go the other way around. So this is a different form of it than what they stated, but essentially the same thing. That this is sort of saying that you can go from any composed search problem to a monotone function, and the depth of the monotone function will be lower bounded by the randomized complexity of the composed search problem. Okay, so G is a two-party function. So G is the inner function, and F is an unsatisfiable C and F on n variables, M constraints. And there's an explicit monotone function F, where the number of variables is M times the size of x to the d. So that's going to be roughly M in our case, such that the monotone depth is lower bounded by the randomized complexity. So this means that, as long as we can get lower bounds for any composed search problem, we'll get monotone depth bounds. And so that's why we get for free this corollary. So if we start with this graph G that I told you about that has very high critical block sensitivity, then from our theorem we get that the randomized complexity of solving the search problem is very large, n over log n, and then you immediately get that the monotone depth of a related function is the same.
So here we don't suffer from the problem that KW gains have, that the randomized complexity is always small.
Right.
Because of the composition.
That's right. Yeah.
How is the compositions developing?
Good question. Yeah. Okay, and then again, same idea. Using the pebbling formulas gives you the other corollary, which is the monotone depth hierarchy separation.
I'm sorry to go back.
Yeah, sure. Yeah.
No, just it's because it's a monotone. It's just because
It's the other direction.
Yeah.
I think it's because it's the other direction.
No, but anyway, you get randomized lower bound just because they are monotone related, not because of the composition.
Sorry, I thought you were right before. So say it again.
Can't find
So
the
you're
right
asking.
whys.
So no. You're asking why.
No, why can you get the lower bound on search problem? In the KW setting, in the non-monotone case.
Oh, it's because it's monotone. Yes, I'm sorry.
This
I'm
is
sorry.
monotone.
Yes, absolutely. This is only working. Thank you. Sorry. Yeah. So in the non-monotone case, you can do everything with randomized. You can solve the search problem associated with a function always with quick randomized things. So this is not going to work the way this only works in the monotone case. Yeah. Sorry about that. Anybody questions? Okay, so like I said, this is, so now if we start with the pebbling examples, and I told you that the randomized complexity of the composed search problem where you start with the pebbling CSP and compose it with a good choice of the inner function G, that then you get randomized complexity square root of n. And there's also an upper bound, so the decision tree complexity of the composed thing is also order square root of n. Okay, and because you have these matching upper and lower bounds, you can prove, and you can use what's it called, padding, to prove that that every level of the hierarchy is distinct. So there's an explicit function f, and again we get this function using the Ross-Mackenzie transformation. Explicit monotone function f on n inputs with poly-size monotone circuits and monotone depth square root of n. And you get the poly-size monotone circuits. The upper bound uses the decision tree complexity. So that's why we used pebbling, because you want a tight result here. And you want it to be something like square root of n. And again, we're just improving. I mean, the real contribution is this is a much simpler proof. The original bounds were slightly worse, but I think Ross-Mackenzie, I didn't calculate it, so I'm n to the epsilon. And then there was a paper into the 1 over something. And then there was a paper with Yuval Filmus and Robert Robert and Steve Cook where we get n to the 6th. So anyways. And you have a paper that gets something too. I'm not sure what your number, probably the same as us, n to the 6th.
No. I think it would be hard for us to get 169. I think
Oh, okay.
like Ross-Mackenzie's 1 over 100.
Oh, okay. I'll skip this. So again, we use the nice properties of G to also show that you can improve all those monotone bounds to average case bounds. The application that really got me going on this was proof complexity. So I'm just going to talk really briefly about this so I can get to the proof. But it's a bad name, but t-CCK proofs, I'm not going to define them at all, but they include, so you can think of them as proofs, refutation systems where you start with polynomial inequalities of degree k, okay, and you can derive a new polynomial inequality of degree k from 2 previous ones by any sound inference, okay? And you just keep doing this until you finally want to get to the inequality 0 is bigger than or equal to 1, okay? So it's a semantic proof system. It's actually defined more generally than that, but it's not worth going into. But they're strong proof systems in the sense that they include lots of these semi-algebraic proof systems that people are studying now, like Lasserre, also called SOS, and the dynamic version of it. If you don't know what they are, don't worry about it. Anyways, it's a relatively strong proof system, quite a bit stronger than resolution. And I've been trying for a while to get lower bounds, rank lower bounds, or tree size lower bounds for these proof systems without using like really special purpose machinery for the particular unsatisfiable formula at hand, like a general method that you could plug in to get lower bounds. So far with limited success, but finally we were able to, and this builds on a few previous papers, quite a few previous papers that also tried to use this communication complexity approach to prove these rank bounds. But anyways, we get this theorem that there's explicit CNF formulas of size S and relatively small width such that any proof in this proof system requires this rank. So rank is the height of the proof. Okay, so if you were in a dynamic SOS proof system, this lower bound, you should think of the lines as being polynomial inequalities of degree k, where k is like log n to the 1 minus little o of 1. So that's how big the degree can be. And then it's dynamic, so you're allowed to derive things, and then you can cancel high degree terms and derive more things until you finally get to false. And the height of the proof is called the rank.
Height is how many lines do you write?
No.
That's
how many
size.
rounds? It's really how many rounds. So
How many
you
rounds?
derive 100 inequalities. From them you derive 100 more. Or a million.
Or a
more.
million, yeah.
Yeah, but it's how many parallel steps of derivation.
I see.
People care about rank because for a lot of these systems, you can find a proof of rank k and into the order k. So I shouldn't be using the same ks, whatever. Okay, so anyways, so this is really the result that I wanted to point out. So there's formulas of size s where we can get rank that's like roughly square root of s, and it works up to k. K, think of that as the degree of the polynomial. Like I said before, like log s to the 1 minus little o of 1.
And they will follow from the multi-party communication.
Yeah. Yeah, and this is a standard. Getting this theorem from the search problem lower bound is like a standard. It's been known for a while. You just have to do some easy manipulations. And then we also get a length space lower bound. I could skip this. Do you want me to? Anyways, we get a length space lower bound. That's the first known length space such result for these non-constant degree, or actually I think the best that was known before, the best before this I think was just degree 1. So we get the first length space trade-offs for these same proof systems. They're not really great, like they're not, polynomial, but they're still non-trivial. Okay, so good. I left some time to do the proof. So I would like to show you the proof. So I'm going to tell you what the inner function is, what the properties that we need of the inner function, and then show you the reduction to disjointness. Okay, so we call them versatile functions, and they have to have these 3 properties. So first of all, I'm going to be interested in reductions from one problem to another problem, and I want the reductions to be ones that you can do not just in the 2-player setting, but in the number on 4-head setting. So every input x, there has to be a function pi of x that you can apply to it to get the input to the new function. So anybody who, I have z on my forehead and I see x, I can compute the new x without any communication or any help. So I don't know what those reductions are called, but those are the ones that I'm in. When I say less than or equal to, I mean that kind of reduction. It's a projection. It's a projection. Yeah, thanks. Yeah, yeah. Yeah, I mean it's a set of variables, but yeah.
But the set of variable
one variable, okay.
You might as well work over a bigger alphabet.
Okay. Yeah, sure. Okay, so the first property is flippability. We want the negation of f to be reducible to f.
So f is now the g.
Yes.
It's a small function.
It's a small function. So in the past, it was like and, or it would be like the index function, where x would be like 4 bits, and y would be a pointer to one of those bits. And the function would be the value that was pointed to by y in the x string. So that's called the index function. That was very popular. The and function was very popular. And exclusive or, yes. Exclusive or is probably maybe the most popular. Yeah, I'm not going to get into that because I got myself in trouble for that one before. Are you serious? Okay, the second property, which is the most important, is random self-reducibility. So function, this is a concept that's been around, in all of complexity theory, but I don't think it's been used as much in communication complexity. But a function is random self-reducible if you have mappings pi a and pi b. So you have a random variable r, and and you map x to a distribution determined by the random variable r and x. So pi a is a distribution on the first coordinate, and pi b is a distribution on the second coordinate. And you should be able to map xy to a uniform other string x prime y prime that has the same value as xy.
So using shared randomness as layers can simultaneously random self-reduce.
Yes, that's what you want. Exactly.
Oh, but usually in complexity, when you talk about self-reducibility, it means that they can compute the function at one point using few other points.
Yeah.
That's the original definition of random. Then it developed to few.
Okay, sorry.
Cryptography, like discrete.
Yeah, yeah, exactly. Yeah, this is very much like the crypto thing. We just didn't realize it.
The other name for that reducibility is downward self-reducibility.
No, that's
No, I think that's
We
different.
was talking
Yeah.
about local correct. Yeah, not downward. But anyway, that's okay.
And then the last one is we want and to be reducible to our inner function. Okay, so here's a little one for k equals 2. It's so x has a number 0, 1, 2, 3. Y is one of those values 0, 1, 2, 3. And the function's 1 if when you add them up mod 4 you get 2 or 3, and it's 0 if you get 0 or 1. And you can check that this has all the properties. So the and function is just in the upper, let's see, wait, I can be fancy here. That's the and function right there. And then to see then that it's reducible, that the negation of the function is reducible to itself, you just map x to x plus 2 and y to itself. And you know, the 2 is what's changing it. And random self-reducibility, so it's a little bit harder to see. You could believe me, but I'll try to tell you quickly. So you first choose an x prime, y prime uniformly from, you either pick it to be xy or 1 minus x minus y. And if xy is a 0 input, then this x prime y prime is going to be uniform over 0, 1. And if xy is a 1 input, then x prime plus y prime is going to be uniform over the ones, the 1 answers, 2, 3. And then you pick a random a, and you output x prime plus a and y prime plus a. Good. Okay. And then Mika found lots of other ones. I'm not going to go through these, but this was a two-party one, and it's nice because it's only four bits. I guess it's actually 2 bits, but anyways. Well, x has 2 bits and y has 2 bits. But then we wanted a number on 4-head versions of these, so that was a little bit trickier to get, but quadratic character ends up being an example. K pointer jumping is a nicer example. So what we want is a versatile function g on the smallest number of bits possible, because we're going to lose those bits, because we're going to end up with a lower bound that's proportional to the critical block sensitivity of the original function before we composed it. So the smaller the number of bits are that g has to take in, the better the lower bound will be. So anyways, I'm not going to go through this now, but the best that we get using branching programs, basically, branching program construction, is that for k players, we have a versatile function g sub k, where each player gets k to the little o of 1 bits. The total number of bits will be k to the 1 plus little o of 1. That's the best we know of. I don't know if you can do better. But anyways, this is good enough for our purposes. Okay, so now I want to tell you how the reduction goes. So everybody good on what? So we're going to just fix this k versatile. I'm just going to do the 2-player case. So I'm going to fix this on this function. You don't have to know anything about it besides that it has these 3 properties. And we're just going to do the k equals 2 case. And again, what I want to do is I want to come up with a protocol for unique. So I don't know if I told you it's unique disjointness, not disjointness. So unique disjointness is each player has Boolean string of length m, and they're given the promise that either they're totally disjoint or they intersect in exactly one place, and you want to say which of the 2 it is. And this is hardest disjointness. So we want to come up with a protocol for unique disjointness from a protocol for the composed search problem. Okay? And g is the special versatile function that I showed you, and we don't care what s is. Okay? We just know that the critical block sensitivity of s is m. Okay? So I think if you can keep track of this notation, this proof should be easy. So a.
You want to write something out about if it's important?
Oh, maybe, yeah. So pi is going to be our protocol for so we have a fixed protocol for this composed search problem, S composed with G of n, and AB is the input to, and the critical block sensitivity of S is M, okay, and we're trying to solve unique disjointness on this input AB, where the size of A is the size of B is M, okay, and we're trying to reduce it So we're trying to convert it to an instance xy of, of S. Yeah. Okay. And the other notation is alpha or beta. These are going to refer to inputs to the uncomposed search problem S. Okay. So M is the smallest. It's the block sensitivity of the uncomposed problem. So that M is less than or equal to N. N is the input size to the search problem, and then
X and Y are n
yeah,
times.
and then X and Y. So this is like 4.
2n.
I think it's something like 4n, because there's.
No,
Oh, you're right. 2n. 2n. Yeah. Okay. So sorry, I don't know how to get around this, but you have to keep track of these parameters. Okay. So first I'm fixing my protocol pi, and now I want to define a particular function f that realizes the search problem, and f is going to be based on pi. Okay. And so f of alpha, so alpha is an input to S, the uncomposed problem. And what I'm going to do is I'm going to look at the distribution over the xy pairs that are the input to pi that are consistent with alpha. Okay, so there's a whole bunch of xy's that are consistent with alpha, and I look at what pi says on all of those.
Well, alpha goes to X or to Y.
No, alpha is uncomposed. So alpha is the
Oh, so
input to, yeah, I know, it's hard to keep track of. So this is the input to the search problem, okay? And for a fixed alpha, there's going to be lots of xy's that are going to be, where their g values are going to be consistent with the alpha. There's going to be lots of those. And I'm going to look at what pi does on all of those g's. And pi, I'm going to average over the randomness of pi and also over this distribution of xy's that are consistent with alpha. Okay, and that's what, so mu alpha, this is the uniform distribution over these xy's consistent with alpha, and I'm going to take f to be the most popular feasible solution that's returned by pi over all of those inputs. Okay, or again, the most popular is also averaging over the randomness. Okay, and it's a feasible solution, so it's a good one. So I'm going to, if it's a bad solution, I'm not even going to enter it into this game. Okay.
But the uniform distribution is
Only those that agree with alpha.
only those that agree with alpha, but then you get a bunch of answers and some are bad ones and some are good ones.
Yeah,
and among
most
the
are good.
ones you take it.
Right. So you're going to get some bad ones because the protocol pi makes mistakes, but most of the time it does the right thing, so you're going to have a nice selection of good answers, and you're going to pick the most popular of the good answers. Okay? So this gives you one f, that particular f that realizes S based on pi, and I'm going to be interested in that f. So using that f, I'm going to find a sensitive input beta to the search problem S. Okay, so it's going to be some critical input where the critical block sensitivity of f for beta is at least as big as the critical block sensitivity for S. Okay, and because this input has block sensitivity at least m, there's going to be at least m blocks in beta that are disjoint, where they're going to be sensitive. So if I flip one of those blocks, f's going to change values. Okay. People good? Okay. All right, so it's not too hard to show that this protocol pi is going to be able to distinguish between the distribution on beta versus the distribution on, oh, that should be a subscript. So beta to the bi is the input beta where I've flipped all the values in block bi. Okay, and mu beta is a distribution of xy inputs, and mu beta to the bi is another distribution on xy inputs where I've flipped the bi'th block. Okay, and the protocol pi will have the property that if I choose xy from the first distribution, then the probability that pi xy is equal to f beta is going to be quite large. Okay, and that's because beta is a critical input. Okay, so that means that no matter what x, y it is that's consistent with beta, to be right, you have to give that one good answer. Okay, so.
And sorry, what is mu?
Uh-oh, is there a mu? Oh, that's the distribution. Yes. So this is, it's a little bit hard to keep track of these things, but once you do, things are easy.
Oh,
So
okay.
alpha is an input to S, and mu is a distribution over the x, y pairs that are consistent with
Oh,
alpha.
sure.
Yeah. So anyways, the first part is not too hard to see because beta is critical. So if I take an x, y that's consistent with beta, there's only one legal answer for it, and therefore pi on that x, y has to be beta, has to give the same answer as f almost all the time because there's only one answer. Okay, and f will, yes. And on the other hand, you use the fact that the protocol's good most of the time and the fact that we pick the most popular answer to argue that when you pick x, y from the distribution where you would flip the Beath block, now we know that the function value, that the special function we know that in reality we have to have switched answer because beta is critical, and we picked the most popular answer and the protocol was pretty good, so that tells us that most of the time with high probability the protocol pi has to say something different than f of beta. Okay, so the protocol pi can really distinguish between these two cases, when you pick an xy from mu beta versus when you pick an xy from an input where the consistent with beta where the bith bit has been flipped.
It's very much like the reduction from disjointness to matching. So
Oh, is it?
Yeah, only it's much more general, and I guess you get lots of power.
Okay. Okay, so all we need to do now is we have to find, given an input, the original input AB for unique disjointness, we just want to get a randomized reduction that takes AB to an xy such that if the unique disjointness is 0, then xy distributed according to the first one, and if unique disjointness is 1, then xy is distributed according to the second one, and then we're done. Okay? So that's the only goal we have left to do.
Unique disjointness is 0 if the two sets do not intersect, or if they do intersect?
0 if they do not intersect.
Oh, so, and, okay, and unique.
So if it's 1, there's going to be one thing. That should say AI equals BI equals 1.
Okay.
Sorry. Yeah. Okay. So all I want to do now is find a reduction given an AB for unique disjointness on m variables, reduce it to a distribution on inputs to S composed with G, so that in the first case I'm distributed according to mu beta, and in the second case according to mu beta, where if the AI BI or if AI BI pair is the one that's both 1, then it's distributed according to beta where the ith block is flipped. Okay, is that clear? Good. Okay. All right. So so that picture pretty much shows everything, but I'll try to go through it. So, okay. So the input is remember the input is A, B, and in this case M has length 2, so I just have an A1 and an A2 and a B1 and a B2. That's the input to the disjointness problem. And in this case, the critical block sensitivity is 2. That's beta is that string there, 1, 0, 1, 1, 0, 1, 0. And the first block is 0, 1, 1, and the second block is 1, 0. So those are the two blocks in beta that are the critical blocks. And I'm just giving you an example. I picked it. No, I just totally picked it. No. No, I didn't tell you what S is or anything. I'm just trying to show you an example. I don't know, maybe this, depending on how you think, it might be worse to see an actual example. But anyways, so we're going to map A1, eventually we're going to map A1, B1. It's going to correspond to the first block, 0, 1, 1.
Coordinating the disjointness problem is corresponding to a block.
Yes. And all the other ones are we just fill them in appropriately. So the first thing we do is, because we want the and to be preserved, we map A1, B1 to our versatile G, and you know, we want the and, so we want the upper quadrant of G that's doing the and of these two. Don't do anything, because it's just sitting there. Don't do anything.
The G that you use means
Yeah.
that you do nothing.
For 2 players, we do nothing here, really. Yeah. Yeah, so when you do the and thing, this is just saying something obvious. Unique disjointness of AB, if it's 0, then G applied to the output of here is going to be 0 for all I, and if the unique disjointness of AB is 1, then there's going to be exactly one AI prime, BI prime, where you're going to get 1. And then we're going to, just what Avi said, so we're going to map this input to, we want it to correspond to feeding in 0, 1, 1 in here, in these wires. In the second one, we want to correspond to feeding in 1, 0, which is the second block. So this is where we need the fact that it's closed under negation. So if the value is 0, like 0, 1, 1, then we just feed it in directly. And if the value is 1, then we want to do the negation reduction. Okay? Good? And then these other ones that aren't in any block at all, we just make them some pair that has the right value. So 1, 1 is a particular example. So 1 plus 1 is 2. So that's a 1 of the function g. So that's why I'm feeding in a 1 of the function g, because the first bit of beta is 1. And the next bit that's not in a block is 0. So that's why I'm feeding 0, 0 in, because 0 plus 0 is 0. Okay, so that takes me to here. Okay, and then I need a randomized reduction because I want a distribution. So then I use the randomized reduction to map to a distribution.
If you just do the deterministic reduction and
you mean where I don't have this?
yeah, it
Doesn't work at all.
doesn't work.
In fact, I have a paper on that was wrong because of that. No longer a paper. But it doesn't work at all if you don't have a randomized reduction. Okay. So that's it. So it satisfies, you can prove, but it's hopefully, if you understand the reduction, it's kind of clear that if unique disjointness of AB is 0, then xy is going to be distributed according to mu of beta. And if unique disjointness is 1, and AI, BI is 1, then it's going to be distributed exactly according to mu beta, where the ith block is flipped. Because we set it up that way. Good?
You can say why the randomness is essential.
Yeah, so the randomness is essential because okay, here's the fundamental reason. When you're dealing with search problems and you compose them, so if you had a solution to the search problem before you composed it, even though there's many possible answers, you're only going to get one. Okay, the solution to the search problem is going to give you one answer, so you're going to be happy. And then you can argue that it has to change. But when you compose it, then even though you have one answer alpha, you're going to have all these different xy pairs, and they can all give you totally different answers. So you can't argue very easily that you're going to be able to, that the value is going to have to flip. And so that's the fundamental problem. So because you're composing the search problem, you can't really keep track, and because every xy consistent with an alpha could give you a wildly different answer, even in a case where there's just two different inputs that you can't, it's kind of hard to nail down what's happening unless you have this randomized reduction and way of finding, one particular value that keeps changing. Does that help?
One way to explain it, maybe even more convincingly, is to say why, if you didn't use the randomness, that would be easy to solve this problem. There wouldn't be a law now, right?
I don't know what you mean.
We can do a deterministic reduction, and it's useless.
Why? I mean, you know.
Well, I don't know. I think that it's useless.
Oh, really?
Yeah,
I mean, I think it's useless, but I don't.
Useless, but if it worked, it would be better, because then we would only need deterministic law bound on the, communication complexity. It would be even easier. So it doesn't work.
Yeah, but I don't know if that's I don't know how to formally prove that. I just know that I can't, yeah, I don't know how to get a deterministic reduction to work. It doesn't seem like it should work, but maybe we'll talk about it later. Maybe I'm misunderstanding you. So that's all that I really wanted to say. I can tell you, so I didn't say a lot of things. Like I didn't tell you at all, you know, the monotone circuit results rely on this transformation. I didn't tell you anything about that. I didn't tell you, you have to prove that these graphs have critical block sensitivity, whatever they are. I didn't tell you how that goes, but I told you already the main things I wanted to say. So if you want to go to your stock deadline paper, frenetic paper writing, we can stop.